Hello everyone, my name is Linwei Zhai from Xi'an Jiaotong University. This is a joint work with my supervisor, Professor Han Ding. It's my pleasure to present our work, RFID Joint RF and Linguistic Domain Learning for Object Recognition. Object recognition is a promising technique that can benefit lots of applications. For example, it can help us to judge the quality of the food or drinks without damaging it. It can help officers to automatically distinguish contraband goods during security checks. Also, it can improve controlling strategy of robotic arms when grasping items. Traditional solutions like X-ray machine usually employ image processing techniques to recognize the object. Such methods are good at shape recognition, but cannot directly identify the material. Hence, certain objects need to be separately checked further by human or other dedicated equipment. In recent years, various approaches are proposed in the literature, among which RFID-based solutions are popular. RFID are small in size and provide rich channel information, face and RSS, that can benefit fine-grained object material identification. However, state-of-the-art approaches rely on large training dataset to learn the model and have no ability of shape recognition. Motivated by this, we proposed a lightweight, non-invasive RFID-based approach named RFID. We arrange an RFID tag area and put the object before it for sensing, according to theoretical analysis and experimental observations. Due to propagation effect and coupling effect, RFID signals are not only impacted by the shape of the object but also by the material. By constructing a deep learning model, we aim to recognize the shape and material of an object simultaneously, even for unseen shape material pairs. Furthermore, we incorporate linguistic feature and extend RFID to recognize unseen material which are not in the training dataset. Then we introduce our DLN model. We first design a sensing capability enhancement module, which explores multiple dimension profiles to depict the object. We deploy a 7x7 tag array and collect the RSS and face information from 7 channel frequencies and 6 power settings. Thus construct the collect RF data as input. The input are forwarded to the channel attention module, which generates a attention map to learn a better representation and mitigate the frequency selective fading. The output then goes through the multiscalar perceptron to learn multiscalar features from both RSS and face domains. In addition, to make RFID robust to different environments, an environment discriminator is introduced to unlearn the domains and remove the environmental-related features. Above components joined compose the feature extractor module. After that, RFID then conducts the object recognition using 2 branches. One is shape profiling branch, which employs a unit structure. It enables spatial information representation and shape profiling. The other branch employs Xi'an and fully connected layers to predict the material. With such design, RFID learns the concept of the individual shape and material, enabling the simultaneous estimation of such 2 properties, even for unseen shape material pairs. Then we further extend RFID's framework to recognize unseen materials. For example, we have RF signal features of material 1 to 4 in the training datasets, which are marked in different colors in the left side. And we want to determine the 5th material type, represented by the red question mark. Since we do not have RF data of this material during training, traditional training-based learning model is not capable to predict its type. To solve this problem, we explore zero-shot learning method. The core idea here is to exploit knowledge from other available sources for help. Since we can easily get name words of different materials, we propose to utilize linguistic domain features. By bridging the gap between RF feature space and its corresponding linguistic feature space, then we can predict the new material type by similarity measurements. In detail, the pipeline here is: first, we embedded the RF feature and word to the same latent space. Then we introduce 2 loss functions to reduce the distance between RF embedding and semantic embedding from the same material type, and increase the distance between different types. After learning, RFID can predict a new material with its RF input by measuring the distance between its RF feature and linguistic domain features. We implement the system with one image reader, for antenna and 49 UHF passive tags, and collect data from 5 different environments, 21 different material types, and 12 different shapes. We evaluate the system performance using 2 metrics, accuracy for material identification and IMWUT for shape profiling. From results shown in the middle figure, for overall object recognition, both the material identification accuracy and shape profiling exceed 99%. For unseen shape material pair recognition, we can see the average accuracy and IMWUT reaches about 92% and 97%, respectively. For unseen material estimation, our system achieves 92.9% for unseen material prediction. In this work, we proposed RFID, which can recognize the shape and material of an object simultaneously, even for unseen shape material pairs and unseen material types. Thanks for listening. For more details, please refer to our paper.